Okay, where we left off, we were about to do the types of mixtures. There are homogeneous mixtures and heterogeneous mixtures. One thing to keep in mind about mixtures is that the composition can always vary from one sample to another for a mixture. The question is whether the composition can vary within a sample of the mixture. Okay, so for heterogeneous, homogeneous or heterogeneous mixtures are distinguished by the fact that the components in the mixture do not mix evenly. So there's more of one thing in one place, more of something else in the other. And so, as I said, the composition can vary from one sample to another, as it can with all mixtures. But the composition can also vary within a sample for a heterogeneous mixture. And some examples of that would be, say, wet sand or sand in water. Sand doesn't dissolve in water, it basically sinks to the bottom, and that's why we have such nice beaches all over the world, which we wouldn't have if the sand did dissolve in the water. So that's a heterogeneous mixture. If you put a spoonful of sand into a glass of water, the sand eventually is going to settle to the bottom, and at the bottom you'll have mostly sand and only a little water, and at the top you'll have mostly water and only a little sand, or maybe no sand. So the composition is varying within that sample of the mixture. Another example might be dirt or rocks. A lot of times with dirt or rocks, you can actually look at it, and with the naked eye, you can actually see little inclusions of different stuff. And that's kind of the definition of heterogeneous mixture, is when there's different stuff in the mixture. We are heterogeneous mixtures in that, there are some areas of your body that are mostly bone and very little muscle, other areas that are mostly muscle and very little bone, and so on. And so, definitely a heterogeneous mixture. Sugar and iced tea is an example of a heterogeneous mixture also. Some of the sugar might dissolve in the tea, but if it's iced tea and it's cold, then most of that sugar is going to go right to the bottom of the glass. And that would be a heterogeneous mixture because you've got sugar on the bottom, tea everywhere else. One that people often don't think of as heterogeneous, but it actually is ice water. And you might be thinking, well, wait a minute, ice is H2O just like liquid water is, so how could that be heterogeneous? There's only one substance present. But the thing is, the properties vary from one place to another. The density of ice is less than the density of liquid water, and so it's the change in density that actually makes ice water a heterogeneous mixture. And then there's homogeneous. Homogeneous mixtures are ones where the components do mix evenly. And the composition can vary from one sample to another. But it cannot vary within a mixture. And since the composition isn't changing from one place to another within a sample. Within a sample. Since the composition isn't varying within a sample, that means the properties are not going to vary from one place to another within a sample either. So some examples of homogeneous mixtures would be things like salt water. When you dissolve salt in water within certain limits anyway, the salt will dissolve completely and mix evenly throughout the water. And the water will be just as salty at the top as it is at the bottom. And so that is a homogeneous mixture. You could have another glass of salt water that has more salt in it, and that would also be a homogeneous mixture. So the composition can vary from one sample to another, but it doesn't vary within any given sample. Air is another example of a homogeneous mixture because air is a mixture of gases. It's made up mostly of nitrogen, but with significant amounts of oxygen and smaller amounts of things like carbon dioxide and water vapor and maybe even a little argon. So, and as I mentioned a moment ago, any mixture of gases is a homogeneous mixture. And so air is a homogeneous mixture. Gasoline is a homogeneous mixture. You won't notice any difference in the properties from, within any given sample of gasoline because everything dissolves and mixes evenly in there. And sugar in hot tea. If you put sugar in hot tea, the sugar completely dissolves and it mixes evenly throughout the tea. And as long as the tea stays hot, that it will be equally sweet on the top as it is at the bottom. So that's a homogeneous mixture. If the tea cools down though, then it starts becoming more like iced tea and some of that sugar might start settling out. Because the solubility for most solids in most liquids, like for instance sugar and water, increases as the temperature increases. And that's why you can dissolve more sugar in hot tea than you can in cold tea. Okay, separating mixtures. Mixtures are distinguished from compounds by the fact that the different substances present are not chemically bonded to each other. In a mixture, the different substances present are just physically mixed together. In other words, they're sort of just in each other's presence, but they're not bonded together. And that makes mixtures relatively easy to separate, while chemical compounds, where the substances are bonded together, are much harder to separate. And in many cases, it's fairly simple to separate a mixture by physical means like filtering, or even you might have to resort to chemical means to to separate certain mixtures. And so the identities of the components don't change when they're in a mixture, and you can actually use the properties of those components to separate them. So they have different properties. You can take advantage of those properties to separate them. And that could be chemical properties or physical properties. And some of the ways that you can separate mixtures would be, if it's a heterogeneous mixture, then often you can just decant, which is kind of a fancy term for pouring carefully. If you have sand and water, then you just wait for the sand to settle to the bottom, and then you carefully pour off the water while leaving the sand behind. And you've separated them by decanting. Distillation, if you have two liquids mixed together that mix evenly and they don't separate into layers, then what you can do is check out their boiling points. If their boiling points are not too close together, then you can use distillation. And what happens is the more volatile liquid, that is, more volatile liquid just means the liquid with the lower boiling point, will boil off first. And you can collect it and condense it back to a liquid by putting it in an ice bath, and then you have your separated liquids. Very often it's a case, simply a case like for a heterogeneous mixture with a solid in it, you can do filtration, which is basically just like a coffee filter, where the solid stays on the filter and the liquid goes right through. And so you've achieved your separation. Okay, so that's separating mixture. We have next section 1.4. Physical and chemical changes and physical and chemical properties. Chemistry is all about changes. That's what we really care about. We like to see how matter behaves, and normally that involves some sort of change under given stress. And those phases can be of a chemical nature, or sorry, those changes can be of a chemical nature or a physical nature. And it really comes down to what is changing at the molecular level. If it's a physical change, a physical change is a change basically in the appearance. Or state or a phase change. And this is a physical change, not a chemical change, because the atoms and the molecules themselves don't change. You can think of a physical change as a change in the physical properties. And a good example of that is, phase change. Like I said, phase change would be something like boiling water. In which liquid water becomes water vapor, or H2O gas. Notice that the formula is still H2O. So the molecules actually haven't changed. It's just that now they're in the gas phase instead of the liquid phase like they were before. And that's essentially what physical change is. And the chemical formula stays the same. Now, in some cases, you may not know what the chemical formula is, and you may not know whether it stays the same. But if it does stay the same, then that's a physical change, not a chemical change. A chemical change is essentially a chemical reaction. And be ready, because I love the abbreviation RXN for reaction. Reaction is a word we use a lot in chemistry, so it saves quite a bit of time and effort to use that abbreviation. So if you see that, that's what that means, reaction. Chemical change is essentially a chemical reaction. And it involves a change in the chemical identity and the chemical formula of a substance. And what essentially happens is that you break the bonds that hold the reactant molecules together, and you rearrange them, and you bond the atoms back together in different combinations. So you can also think of it as a change in chemical properties. Changing the chemical identity will change the chemical properties. So say burning something is a good example of a chemical change, and it's also a chemical reaction. So if you were to take graphite, which is actually flammable, and you burn it, the carbon in the graphite, which is what graphite actually is, it's just carbon, combines with oxygen from the air to form CO2. So you had two substances going in, carbon and oxygen, and coming out you have carbon dioxide. That's a different substance with a different chemical formula, and so that is a chemical change. Or the rusting of iron. The rusting of iron is just a combination with oxygen from the air. And don't worry about why we have the 4 and the 3 and the 2 here. That we'll worry about that later. Well, it's actually about the conservation of matter. That is, you have to have the same number of atoms of the same elements coming out of a reaction as you have going in. So we've just made sure that that happens by putting numbers in front of some of the formulas. But anyway, Fe is the symbol for iron. It comes from the Latin word ferrum, which is the Latin word for iron. And it combines with some oxygen from the air, and you get iron oxide, which is rust. This is a chemical change because you had two substances going in, iron and oxygen, and they come out bonded together as iron oxide. Definite example of a chemical change. So looking at the properties, physical properties, physical properties are properties that are observable without changing chemical composition. Okay, so you can look at something and see its color. That doesn't actually change the chemical composition of something, and so color is a physical property. You can smell something without changing its chemical makeup. So odor is a physical property. Shape and size, you can see those without changing chemical properties. The phase or the state of the substance, whether it's a solid, liquid, or a gas, is physical. Melting or boiling points. You can observe the boiling point of water by putting some water in a pan and sticking a thermometer in it and heating it up until it boils. And you're not changing the chemical identity of the water. You're changing it from a liquid to a gas, but that doesn't change its chemical identity. Still H2O. So that's a physical property. Density is also a physical property. And density is defined as mass divided by volume. We'll get to that in a little while. But anyway, mass and volume are both things that you can measure without changing the identity of a substance. And so density is a physical property. And for chemical properties, these are the kinds of things where observing chemical properties changes the chemical composition. Changes the chemical composition of the substance. Some examples would be something like flammability. That would be a chemical property because in order to find out whether something is flammable or not, you have to burn it. And if it burns, then it's going to form a different compound, kind of like carbon did up here. Carbon and oxygen form CO2. So that's a physical change. Or sorry, chemical change. Reactivity, if you're talking about chemical reactivity. Acidity, that is how acidic something is, as opposed to basicity. And toxicity, how poisonous is something. Those all involve chemical changes. These distinctions between chemical and physical changes and properties can be somewhat difficult for beginners to comprehend, but it helps if you think about the composition of the substance at the molecular level. Okay, there are some examples on pages 9 and 10 in the textbook where you can actually see little diagrams of the formation of rust. For instance, on a nail, starts as iron, ends up as iron oxide, or the boiling of water. Starts out as H2O, ends up as H2O. So that's a physical change, while the rusting of iron is a chemical change. And there are some more examples also on the next page after that. Okay, that is officially the end of the lecture for day 1, according to the schedule. I see we've got a few minutes left on the clock, though, so I'm going to keep going just in case we get behind schedule later in the semester. So section 1.5 is about energy. Energy is a part of both chemical and physical changes. You know, boiling water requires heat, obviously. So energy is something that is definitely involved in chemical reactions also. So it's a fact that changes in energy usually go along with chemical and physical changes. So some examples, like a chemical change would be something like the burning of propane. That obviously involves some pretty big chemical or energy changes. And evaporation of water. Evaporation of water is a process that takes in energy. And so that's why it feels cooler when water evaporates from your skin. Because in order for that water to evaporate, it had to take in some energy from your skin, and then it goes off with it, and so it cools you down. Energy itself is defined as the capacity or ability to do work okay. Work, on the other hand, is defined as the action on a force through a distance. In physics, there's an equation that goes to the effect that work is equal to force times distance, which is pretty much what the definition just said. A force pushing something through a distance is work. When we talk about total energy of a substance, we're talking about the combination of kinetic energy and potential energy. Kinetic energy is the energy that's associated with motion. Anything that's moving has kinetic energy. And potential energy is the energy that's associated with, say, the composition of something or its state or its position. Potential energy is stored energy. That's why it's called potential energy, because it's not actually expressing itself at the moment. And it is possible to convert kinetic energy to potential energy and vice versa. If you think of something hitting on a hot, sitting on a high shelf, it has a potential energy is, like I said, it's the energy associated with position. And so something that's up on a high shelf would have a relatively high potential energy. If that object falls off the shelf and hits the ground, it will have a lower potential energy on the ground because it's lower down in a lower position. While it was falling from the high shelf to the ground, it was moving. And so while it was moving, it had kinetic energy, which is the energy of movement. The amount of kinetic energy it expended when it was falling to the ground is exactly equal to the difference between the potential energy on the shelf versus the ground. And so the total amount of energy actually remains the same. We have also thermal energy. Which is associated with temperature or heat. That is a form of kinetic energy. Because the presence of heat or thermal energy causes molecules to vibrate. And the vibration is a movement, and so that's considered to be a form of kinetic energy. And the fact is that everything has a certain amount of thermal energy. Thermal energy is related to the temperature. The higher the temperature, the more thermal energy something has. And the only way that you can get rid of all thermal energy completely is if the temperature were to reach absolute zero. And the thing is, absolute zero is a theoretical temperature. Nobody ever actually has reached absolute zero, even in the laboratory. And it's not likely that they ever actually will, because it's more of a hypothetical temperature. But that would be the only way to remove thermal energy completely. It's an important point also that energy is always conserved. In fact, that is a scientific law. The law of conservation of energy. And some of the things that the law of conservation of energy says is that energy cannot be created or destroyed. But it can be transferred from place to place and changed in form. So, kinetic energy can become potential energy or vice versa. And the total amount of energy in the universe is constant. Okay, so the total amount of energy in the universe is constant, meaning it doesn't change. So if one thing loses energy, something else has to gain that same amount of energy. The energy that something loses may go to several different places, but the total amount of energy gained by all of those different places would be the same as the energy lost by the original object. And so that's what we mean. And that's what I was getting at also when I was talking about the book falling from the shelf. The amount of kinetic energy it expends on the way down to the floor is exactly equal to the difference in the potential energy when it was sitting up on the shelf versus sitting on the floor. Okay, so that would be conservation of energy. So that basically is what conservation means. It's not like an ecological term, meaning, don't use any more energy than you have to, although that's a good idea. That's not what we're talking about here. We're talking about the fact that energy cannot be created or destroyed, and the total energy in the universe remains the same over time. Also, one thing to remember in chemistry is that generally when we speak of things that have high energy, we're talking about something that's unstable or reactive. Those are both terms that correspond to high energy. And in practice, systems usually change in ways that lower the energy content. So, and that means basically that systems tend to go from less stability to greater stability. Nature generally favors greater stability, which is just another thing, a way of saying lower energy. If you think of yourself when you've had a lot of caffeine and a lot of sugar and you can't sit still and you're bouncing off the walls, well, that's a pretty high energy situation, and it's also pretty unstable. Whereas later on, when you crash from all that, and you just don't want to do anything other than just sit on the couch and watch TV, that's a very low energy situation, and it's also very stable. You're not going to move. Okay. The object falling from the bookcase tends to reduce the potential energy of the object. So that is a favored process also. This can also be observed in the potential energy held by chemicals in chemical bonds. Potential energy is important in chemistry, not so much for how far off the ground something is, but rather for the amount of energy that's stored up in chemical bonds. That is also considered a form of potential energy. Okay. So chemical energy is also a form of potential energy. It doesn't look like a P, but it is. All right. You can look at an example of a chemical reaction where you say burn propane. C3H8, that's propane. When you burn it, it reacts with oxygen from the air, and you get carbon dioxide and water, and a large amount of energy, known as heat, in the form of heat. Propane is high in energy. Potential energy is chemical energy, and that makes it unstable and reactive. Same is true of oxygen. Oxygen is very reactive because it has a large amount of potential energy stored up in its bonds. Okay, carbon dioxide is lower in potential energy. Which means that it's more stable and less reactive. Okay, same is true of water. It has lower potential energy than the reactants do. It's more stable. And it's less reactive. And that's why the reaction gives off energy. If you were to take the total amount of energy given off as heat in this reaction and add it to the potential energy held in the bonds of H2O and the potential energy held in the bonds of CO2, and you compared it to the potential energy in propane and oxygen, you would find that the two energies on either side of this equation are the same. So these two chemicals had so much energy in them that they can produce these two chemicals and give off a bunch of energy besides, and still have it be the same total amount of energy as you started with. And that is an example of energy changes in a chemical reaction. The energy changed in the chemical reaction can be used to do work, like to heat a house or to cook food or to move a car. But it takes energy to do work. And this is part of the problem with the greenhouse effect also. The fact that carbon dioxide is such a stable compound, it's really hard to change it into anything else. In order to do that, you would have to add a lot of energy to force carbon dioxide to be something else. And in order to do that, well, producing that energy would probably produce even more carbon dioxide. So it's kind of a vicious circle. Okay, anyway, that's the end of our preview of energy in chemical reactions. And I went a little over time, but we covered an extra section. So we're doing pretty well on the schedule. We'll start out with section 1.6 next time. And until then, see you.